Imagine a sheet of material so thin that it is only a few atoms thick, and yet can guide light as if it were a laser beam running across its surface. That's what flat hyperbolic polaritons do, hybrid particles of light and matter that behave like highly directed rays within two-dimensional materials. And most fascinating of all, these rays don't need lenses, wires, or circuits. Just a bit of atomic scale design. This breakthrough has been published in the journal Nature Communications by researchers from institutions such as the University of Minnesota, the Indian Institute of Technology Bombay, Purdue University, City College of New York, and the University of Zaragoza. Today, in one step, I'll tell you how they work, what materials make them possible, and why they could change the way we guide light, control heat, or even process quantum information. What is a polariton? A polariton is a mix. One part is light, another part is matter. It's as if a photon merged with a material vibration, like a phonon, a plasma, or an exciton, and became something new. The interesting thing is these hybrids can travel across the material's surface with properties unlike common light. They move slower, bend, and can be confined in tiny spaces. In some materials, polaritons move circularly, like in graphene, in others, elliptically, like in black phosphorus. And in certain extreme cases, they are hyperbolic and flat, as in molybdenum trioxide. What does it mean for them to be hyperbolic and flat? In many materials, light propagates in all directions. But in certain crystals, due to their internal structure, light can only travel in specific paths, forming curves called hyperbolas. When that happens in a single layer of atoms, we say we have planar hyperbolic polaritons. And that's where magic begins. These light rays behave almost as if they were straight lines in an optical circuit, but within an atomic material. How are they generated? They form in materials that are anisotropic, that is, they behave differently depending on the direction. Depending on the interaction type, we can have three kinds of 1. Plasmons, which are free electron oscillations. 2. Phonons, which are materials' internal vibrations. 3. Excitons, which are electron-hole pairs bound by attraction. Materials like tungsten telluride, molybdenum trioxide, hexagonal boron nitride alpha, or black phosphorus are great candidates. How are these rays observed? Scientists use special microscopes with metallic tips to launch these rays onto the material and then see how they propagate. Techniques such as scattering, near-field microscopy, or photo-induced force spectroscopy allow visualizing the paths followed by light trapped in these materials. Can they be controlled? Yes, and in many ways. Rotating atomic layers, as in the famous magic angles, adding atoms or metal ions, stacking different materials, or using materials that are ferromagnetic or ferroelectric. Thus, rays can be redirected, focused, turned on or off as needed. And what's all this for? These polaritons can revolutionize many areas. For example, in quantum computing, they enable control qubit interactions. In heat management, they efficiently transport energy by radiation. In chemical sensors, they detect molecules precisely due to light confinement. In advanced optics, they focus light in sub-millimeter spaces beyond the classical limit. In polarization control, they manipulate light vibrations to create ultra-thin optical devices. Light was long difficult to control on a small scale, but now, thanks to flat hyperbolic polaritons, we can guide it, confine it, redirect it, and even make it interact with individual atoms, all within a layer just a few atoms thick. From fundamental physics to futuristic devices, these tiny rays can have a huge impact. This was a step towards a new way of seeing light. If you find it interesting, don't miss the next video.